locomotion is a beautiful mobility. If you look at this dog running, its nervous system is solving an amazingly complex control problem. It's coordinated more or less 300 muscles in a perfect way, perfect rhythms, and it's solving a very complex control problems because it's very unstable, it has to keep balance, it has to move forward, it's center of mass. So it's amazing how beautiful animal locomotion is. So the main components behind this is, first of all, the mechanics. The biomechanics of the body is very well designed to already simplify part of the control problem. Then you have the spinal cord, which is very much let's say, the computer for locomotion in vertebrate animals. You see there very interesting circuits like reflexes, very fast sensory motor loops that coordinate what happens in the body and what happens with the neural circuits, like handling perturbations. And these very interesting circuits which are called central pattern generators. These are neural oscillators, all distributed in the spinal cord, including in humans, and they are well coordinated to already provide by themselves oscillatory patterns necessary for muscles. And finally, you have higher parts of the brain that will modulate the activity of the spinal cord for step planning, for visually guided behavior, and for steering. But for me, the head is just a nice addition. You don't really need it. And an extreme example is you can cut the head of a chicken, and it still runs for a while. So for me, the brain is overrated. The spinal cord is really the thing to study. And if you look at the spinal cord and the biomechanics, it's interesting how it has evolved. So if you look at very simple vertebrates, like eels and lampreys and salamanders, these are very simple animals. They rely a lot on these neural oscillators. They are called central pattern generators. And the more you go to mammals, the more it's sensory-driven, because it's more unstable, so reflexes become more important. And of course, descending modulation. The brain is still a bit useful, so the descending modulation becomes more important. But understanding how all these components interact is very complex. So there are very complex relationships between the reflexes, the body, the environment, and the CPGs, the central pattern generators. So my message today to you is we need robots. We need robots to investigate this. So robotics and biorobotics is a very cool field of research. So many very exciting biorobots being developed, legged robots, ETH, a wonderful quadruped robot here in Zurich, many others. And people have made also exciting flying robots, exciting swimming and crawling robots. And this is a very exciting field of research, very interdisciplinary, many people interacting in very useful ways. And especially what I like is this loop. So first of all, taking inspiration from biology to develop new ways of controlling robots and new morphologies of robots. And the big goal clearly is to go outdoors, places where wheels and caterpillars have trouble. Water, mud, sand, that's where you need bio-inspiration. And nature has found wonderful solutions for this. So if you want to do outdoor inspection, agriculture, transport, research and rescue, it's really meaningful to take inspiration from biology. But then one thing I really like is this feedback loop, how a robot can become a scientific tool. And there's amazing work being done, and you see here on the right, robots to study neuroscience, to study biomechanics, and study high dynamics. And this is really what excites me and what we're doing in my lab. So coming back to this question of how these different components have changed during evolution, what we do is two things. So first of all, we make numerical models of the spinal cord, so both reflexes and these neural oscillator models. And we like to have physical devices to validate them. Of course, you could simulate bodies, but having real physics, real swimming, real everything is better. So here, a robot makes sense to be used as a tool. So let me show you some examples. So I will start with the salamander. I think everybody knows the salamander. A salamander is a very cute animal. So this is a robot, by the way. But in general, a salamander is a very nice animal because it's a very old animal. And it has made this transition. It's a kind of key animal from the transition from swimming to walking. And what we discovered together with neurobiologists is how amazing the spinal cord is organized. So it's really beautiful. You only need very simple signals coming from higher part of the brain. These are the red arrows behind me. And just by modulating two signals, you can change speed, you can change heading, turning, and even type of gait. So it looks like in a salamander, if you stimulate your spinal cord at a low level, you're walking. If you stimulate a bit more, you accelerate. At some point, you pass a threshold and you swim. Just amazing, just passing the gas pedal, complete change of circuitry. And this shows that basically the spinal cord is amazing. It's really sophisticated and really simplifies control for other parts of the brain. Now, while doing that, we got a phone call at some point from the BBC to say, hey, you're making cool robots, could you make a crocodile robot for us? And of course, yes, we want to make a crocodile robot. So we had fun interacting with them. It's a documentary called Spy in the Wild. So this is a robot. So they made a wonderful skin, and they have many cameras on board, and the idea is to use these crocodiles to film wildlife. And here you see Tommy's lab, PhD student in my lab, remotely operating the crocodile robot. And for us, it was a very interesting exercise to see if our robots could go outdoors, could go in Uganda, this is close to the Nile, and be used to observe nature and wildlife. So very interesting exercise and very fun to do. And I really recommend, please look it out. Spy in the Wild is really a wonderful documentary. Now coming back to the science, so if we go to mammal locomotion is more challenging. The center of mass is higher, support polygon is smaller. And for instance, if you look at the cat, it's both a challenge and an opportunity. You're more agile, but you have to be more careful how you do your locomotion compared to salamanders. So what we're interested in exploring is how the biomechanics are wonderfully designed in animals. So if you look at the biomechanics of a cat, the musculoskeletal system, you find very nice properties. So first of all, the limbs are lightweight, very little mass, most of the muscles are in the trunk. Then the limbs are very viscoelastic, meaning they can take impacts and dampen the movements. They can store energy in elastic components. And finally, as a first approximation, the limb is like a pantograph. You have the highest segment and the lowest segment that tends to stay parallel. And these are very interesting properties because if you use them properly, you can really simplify locomotion. And that's what we did. So let me present you Cheetah-Cub, a cute little robot, so very lightweight. And it was used to implement these three properties and see how and if and how it could simplify the problem of locomotion control. And first, it was a very interesting exercise. So we managed to have a little robot moving fast, and the kinematics, as we say, the joint angles are very close to what a real cat would do. But the exciting part for us was to show and demonstrate how stable it is. So if you make a small perturbation going down a step, we were expecting you need fast control loops to stabilize that. Of course, if the perturbation is big, you need it. But for small ones, just the mechanics are right. And this is a very important message from biomechanics and robotics to neuroscience. They don't underestimate your body. Your body is well designed to do locomotion. That was the message of this paper. Now, what about human locomotion? Human locomotion is even more complex. The center of the basin of attraction, here the support polygon is very small, center of mass even higher. And interestingly, we don't know much about the spinal cord organization. It's very hard to record neural activity in the spinal cord. We don't know much about the spinal cord of humans. So here again, modeling can be amazing. So you can model the reflexes. It looks like human locomotion, much more sensory-driven. And you can model the oscillators, the CPGs. And together with the mechanics, you can find very nice circuitry and explore very systematically what's the right trade-off between what's called feed-forward control and feedback control, between sensory response and the central pattern generators. And here we could show that we have the two together are wonderfully coupled. They can have very simple control of speed. You just need to change a few signals. Again, higher part of the brain, not too useful. You just rely on your spinal cord to do locomotion. And interestingly, you can bring this to robotics, back to robotics, in the sense that by running in real time the whole circuitry of the spinal cord, the muscles, we can extract torque signals to simulated motors. You'll understand why it's simulated. So we simulate the physics properly. But then you have all the reflexes and all the right responses provided by you by this virtual spinal cord. And here showing, indeed, your spinal cord does a good job for you. You can rely on it a lot to do locomotion. Of course, if you're a bit nasty, you need more. And as you'll see here, if you have a big perturbation, you're in trouble. Here, the higher part of the brain becomes useful, either for avoiding the obstacle or the disturbance, or to stand up. You need higher part of the brain. So don't give it up, but otherwise rely on your spinal cord. So now, how does it relate to spinal cord injuries? That's clearly dramatic. If you lose communication between higher part of the brain and the spinal cord, it's dramatic. It's really frustrating. The spinal cord could still be functioning, but you cannot communicate with it. So one approach to solve this is the neuroprosthetic approach, electrical or pharmacological stimulation of the spinal cord. And there's wonderful work being done by colleagues in the Center of Neuroprosthetics at EPFL. So Grégoire Courtine, Silvestro Michera, or Stéphanie Lacour, they really work on direct stimulation of the spinal cord, and they have amazing results. Now, an alternative approach is to use a device like TWICE. This is an exoskeleton where you can have a kind of wearable robot that moves you. And this can also be a very promising approach because you can take it on and off. It's like a legged wheelchair. And with TWICE and many now companies are doing this, you have really had the opportunity to do locomotion with these external devices. And some of you may have had the chance to assist to Cybathlon, this amazing competition of different assistive devices in Zurich. Here you see Silke Pan, she's the pilot using the TWICE. And in that competition, the teams had to solve the problem of doing a parkour. So a good way of promoting development and discovering it's still difficult, but really amazing results on paraplegic pilots controlling this. So what we do, of course, the hardware, you can start buying it. There are companies doing it, and TWICE is a startup from EPFL developing it. But the control part is still very challenging. How do you interface with the remaining functionality of the pilot? So one very promising approach is to reuse everything we do in simulating the spinal cord and use it in real time as a controller for the exoskeleton. So you can simulate the muscles to have like elasticity. You can simulate the spinal cord circuitries, especially the reflexes, and the central pattern generators, extract torque and apply them to an exoskeleton. And we do that in this European project called Symbitron. So it's many partners in Europe working together on this. Very exciting. And these were some of the first results we got. So we're managing, indeed, to run in real time the spinal cord circuitry, the simulate muscles, extracting torques, applying them to the torque signals, applying them through motors to a paraplegic pilot. And what the pilot has to do is basically shift a bit balance from left to right, but then he or she could really rely on the virtual spinal cord to trigger the next steps. And we feel this is a promising way of doing this. Especially because if you do this properly, you can still benefit from the spinal cord circuitry, the simulated one. You have reflexes correcting steps. And here in this movie, you see little push or pulse, perturbation being applied. And each time you see a reflex kicking in, correcting the steps, exactly like in the simulated robot movie as before. And that's really our dream. This is now very recent work, 2 weeks ago, where on a wearable robot, we like to apply this virtual spinal cord and really help to restore locomotion with a person who is completely paraplegic. And the big hope is that by having this virtual spinal cord, you have the reflexes and the patterns that you normally get from an intact spinal cord, and through the exoskeleton, like TWICE, be able to locomote again. So I started my talk saying this nice link between biology and robotics, and I think we should add medicine in this loop. And both in my lab, in many other labs, I think that it's a very exciting times where you have very cool interaction between biologists to study and understand mobility, roboticists to do the engineering of the mobility devices, and possibly most important, medicine and rehabilitation experts to restore mobility. And I really hope that devices like this will restore locomotion for people who need it. Just to conclude very rapidly, this is teamwork. We need many people to do robotics, so I'd like to thank the team. They really worked hard on this. I'd like to thank the funding. And two people here, especially here, Amy Wu, she's the postdoc. She did all the modeling and the controls. She's in the room, so she'll be welcome to talk about it with you. And Tristan Vuga is the designer and of this TWICE, and he launched this startup. So please discuss with him as well. Thank you very much for your attention.